Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
Hello, and welcome to the MIT Faculty Forum Alumni Edition. My name is Jordan Wirfs-Brock. I'm a data journalist at Inside Energy, so I'm very excited for today's topic, which is all about energy systems and the electric grid. As a reminder, this is an interactive forum, which means a key ingredient to the success of this event are your questions. They make this happen. So here's how you can submit your questions. Below this feed, there is a Google form that will allow you to type in a question, and we will see that and get that question to our panelists. You can also submit questions using the hashtag MITBetterWorld on Twitter. We'll be monitoring that. And we will try to get to as many of the questions that we can. So today, we have three great panelists who will be talking about their research on energy and considering innovations in technology in areas like power storage and how that may change the way we consume energy, the way we think about energy in the coming years. So our guests are going to start out by sharing some of their research, and then we'll get to your questions. So we're going to start with an introduction from each panelist. So you'll have a few minutes to tell us about your research and about the innovation happening in your field. So we're going to kick this off alphabetically. Our first panelist is Michael Bradley. He's an associate professor of physics at the University of Saskatchewan. Michael, take it away.
Okay, well, thanks very much. Yes, I'm Mike Bradley. I'm a professor of physics and engineering physics. We have a long name for our department here at the University of Saskatchewan. And as an applied physicist, I'm mostly involved on the research side in terms of sort of things related to future energy production. And we have one of Canada's larger plasma physics laboratories here. And actually, that makes us similar to MIT in a sense. Of course, we're on a much smaller scale. But in our plasma physics lab, we pursue two different aspects of energy production. One is semiconductor processing applications. People may or may not know that the majority of the solar photovoltaic cells that are used in solar installations are, well, they're semiconductor devices, and of course, a major part of the fabrication steps in any semiconductor device utilize plasma processing. So that's one area of research that we're very involved in, and with a view to improving the efficiency, for example, of solar photovoltaics. The other branch of it is the sort of further longer-term scale, which is nuclear fusion. I mean, everyone's heard of that. That's a process whereby light nuclei are fused with the release of energy, and it's certainly an intriguing and exciting prospect for power generation. We're not there yet, of course. And just, it may seem a bit funny because we're spanning the space, but if you think about it, the solar power we get now is in fact fusion power, because the sun is a great big gravity-driven fusion reactor. And so, in fact, there's not, I mean, in some fundamental sense, especially from a physics point of view, these are kind of the same process that is going on. So that's a brief overview of the research. I'll just show you, I'll give a shameless plug for our lab. I'll try to share my screen here if I can. So this is, let's see, okay. This slide just shows you our, can you see that okay?
Yep.
Yes.
Oh.
So here's our province, Saskatchewan, north
Mike,
of...
it went away for a second.
Oh, I'm sorry.
It was there and then it popped off.
Can you see now? Or let me try again. Little technical issue here. How about now?
Yep.
Okay. So there's a little inset. Okay. So there's a little inset map of our province. We're north of Montana and North Dakota. We're a province of about 1.2 million people. We're growing quite rapidly. And in fact, I mean, I work on the research side, but our power grid is actually under some considerable expansion as well. Every year we set a new record. And there's also a commitment by our provincial utility to increase the renewables portion of our power to about 50% by 2030, which is pretty ambitious. So these grid storage issues are going to be relevant for us too. We're mostly coal and natural gas powered right now because fusion isn't ready, of course. We do have wind power installations, and also there's a plan for more solar in the future. So that's a little bit about our provincial situation. And then on the sort of right-hand side of the slide that I'm showing, you can see a number of our plasma processing machines for semiconductor processing, as well as Canada's only small tokamak fusion device. So that's a little bit about me and where I come from in this sector. And hopefully that's good for an introduction.
That's great. Thank you, Michael. Up next, we have Ethan Crumlin. He is a research scientist at Lawrence Berkeley National Laboratory. So Ethan, a couple minutes, introduce yourself and your work.
Great. Thank you very much, and welcome everybody, and thank you for attending. So my name is Ethan Crumlin. I'm going to just try to do a screen share as well and walk through a few slides. And then, is it showing?
It is. Yep.
Okay, great. And so, still on?
You're good.
Great. And so what I do is I work at the Advanced Light Source, which is a synchrotron facility in Lawrence Berkeley, California, Lawrence Berkeley National Lab in California. And it's essentially a third-generation facility where we do a lot of X-ray science across a wide range of tools. And so this is in general what a synchrotron facility will look like. It generally has a LINAC, which will accelerate some electrons. It'll go around a booster ring, and then it'll go into a storage ring where essentially the rotation going around the ring creates these X-rays. And we use these X-rays to do a wide range of characterization. Most people are familiar with them with regards to doing X-rays for their own teeth, and they can see through and see the bones or something that's maybe broken. We use them for very different things here, which is to do material characterization. And so there's a lot of different synchrotron facilities around the world, and these are just 4 of them that I want to highlight across the country. And the one where I'm working at is the one in Advanced Light Source, which is in Berkeley, California. And these are all user facilities. So these are facilities that anybody that has an interesting question that they want to answer from a material science perspective around the world can apply for beam time and to do some form of science and characterization at these facilities. And so the technique that I specialize on is what's called ambient pressure XPS, so X-ray photoelectron spectroscopy. Generally, this is an ultra-high vacuum tool where it's a very low vacuum, essentially the vacuum lower than space. However, what we want to do when we look at energy materials is look at how these environments, these materials are working in the environment they're actually working on. And so what we've done is through innovations that have happened in the field, especially largely done at the Advanced Light Source, is to add some differential pumps, some optics, where we can actually operate in an analysis chamber, we can actually have a gas. And then some later innovations that we've done recently that I've been helping to pioneer is to do higher pressures where we can actually do these studies with a liquid environment. So now we can look at not just a solid gas interface, but a solid liquid interface. And we can do all of these under operational conditions, such as applying potential. So this is fantastic for being able to look at electrochemical systems, for example. And so with this, we have the ability of looking at a wide range of different techniques. And this is based off of the energy range that you might use to probe a solid liquid or solid gas interface. So if you use soft X-rays, something below 1.5 keV, you have the ability to look at more of the solid gas interface. And when you go to harder ones, you can look at the solid liquid. And so this is really great for the water splitting, the corrosion, the fuel cell and catalysis work. And these are actually what some of these end stations equipment look like. These relatively large metal, loud, sometimes vacuum equipment where inside you'll put a sample. This is one that looks like for a solid gas sample where you'll be able to run and do the studies. And we've done this for a few things. So one is a lithium air battery where you'll have the ability of having much higher energy storage potentially with the fact of actually combining lithium with air and oxygen. And so this we made a solid state battery for and to do this kind of characterization. And from this you can actually set up in the sample, run experiments, look at how the sample surface is changing when you're applying applied potential. And this we can, Yes.
Ethan, I'm going to jump in just for a second because I think we're still seeing your first slide, and it sounds like you've got some really great visuals. So if you could advance those for us. Thank you.
Oh, do you see them now or no?
Yeah, yeah.
Oh, sorry, I was going through. Okay. Yeah,
Perfect.
sorry. Let me just show this one. This is what advanced light source looks like. So, oh yeah, sorry, I wish, yeah. Okay, so we'll just continue. And so this is what it looks like inside a chamber where we're doing the sample configuration. And so we'll have a sample that'll be located in the center. We'll be able to do x-rays that are coming through, and this is what we'll be collecting. And these instruments, and then so the newest innovation that we have now is where we're actually able to do solid liquid interface. And so this is a little movie where you can see what it'll look like when we're actually preparing this. So we have a liquid environment now, and we'll dip down our electrodes, and then we'll pull them up and position them from the cone. And what this will allow us to do is look at a solid liquid interface as long as we have a wetting environment between the sample we want to look at and the liquid we want to look at. And this is kind of the newest innovation, this technique of science and material interfaces, is to try to look at this. And this allows us to look at, this is, for example, we're doing water splitting, so we're creating hydrogen and oxygen, and we're probing the solid liquid interface while the reaction is taking place. So we can see this chemistry evolve all together. And what this most recent work that we've been able to do is leverage this to look at what's called the electrochemical double layer. So this is kind of a fundamental property that exists between all solid liquid interfaces. And we can see the potential drop across this interface using this technique. And we kind of did this with a few different tricks. So one is to just look at how the interface works, and we can get the potential sensitivity of this drop and measure this and extract out the information. So we're able to essentially regenerate what the electrochemical double layer looks like and confirm a model that was kind of hypothesized about 100 years ago. And so that's the high level of this. And if there's more questions or want to see more of the slides that we missed earlier, we can do that too. But thank you.
Thank you. And our third panelist is Warren Powell. He's a professor in operations research and financial engineering at Princeton University. So Warren, take a few minutes, tell us about your work and what's exciting in your line of research.
Great, thanks, Jordan. So when I graduated from MIT, the hot topic was the trucking industry, which had just been deregulated. And 20 years of doing that taught me how to optimize large-scale systems under a lot of uncertainty. And then around year 2002, 2004, I started shifting gears into energy and suddenly found that everybody was interested in my ability to deal with uncertainty. So I leveraged all my trucking stuff, moved over to the energy world. Okay, let me see. Okay. So does everybody see my fancy slide of the grid?
Yes.
Okay, so the North American grid is that is north of Mexico, is divided into 4 big chunks. One of which is called the Eastern Interconnect, which is the biggest. There's a Western slice, which is mainly the West Coast. There's Texas, being Texas because, well, Texas is sort of runs its own path. And then there's Hydro-Quebec, which is tucked away up there in Canada with a tremendous amounts of hydro, which we, of course. Now, the Eastern Interconnect is so big, it's further carved into smaller pieces. The piece that deals with my part of the world is called PJM Interconnections, and it covers the mid-Atlantic states out to Chicago. And every single day, in fact, right around 15 minutes ago, they fired off a big computer model to plan coal, nuclear, natural gas, which has to be planned a day in advance because all of this involves boiling water, and that takes time. Then you have gas turbines. Those are planned more like half hour to an hour in advance. They have a bit of wind. It's not a lot, but I'm going to talk about that. And we're talking about offshore hydro. We did a offshore wind. We did a large study with the Department of Energy on that and learned a lot. And we do have a bit of solar. Not well known to the world is that New Jersey is called the Sunshine State. And that's because, like Germany, we simply decided we were going to do a lot of solar. I think we're second, maybe second or third in the country to California. So the challenge is now we have a mixed portfolio with decisions that have to be made a day in advance, where you can say the nuclear has to be made a year in advance, to decisions that have to be made an hour in advance, to wind and solar, where it's not a decision, you're just forecasting. We do have a bit of hydro, but it's a very small amount, and they just pump uphill at night and downhill during the day. So if you take the PJM wind farms, they have about 5 gigawatts of capacity. So you see it maxing there at 5,000 megawatts, but this is a year's worth of wind. You see a strong seasonal effect. It drops down during the summertime. And then, of course, you see the usual variability. And this is not one wind farm. This is all of them. If you break it down in a 30-day increment, you can see that the wind is going from as much as the 5,000 megawatts down to 1,000 or even 0 in fairly short periods of time. This is not easy to forecast. Now, here in New Jersey, we have a big utility called PSE&G. And this is, they have 23 utility scale solar farms. And this is a year's worth of energy. Once again, you see it dipping in the wintertime. The wind dips in the summertime. And by the way, it may not be a big mystery, but even here in New Jersey, the sun does set. So here's 7 days where you see the sun setting. But when the sun's up, you can clearly see the effect of cloud cover. And some of them, like the 3rd day there, it's clearly a very cloudy day. And then you have like the 5th day where it's very mixed sun and clouds. That's very hard to forecast.
Warren, I'm going to pause you for a second. Can you make sure you're advancing your slides? Again, I think we have the same.
So I'm in presentation mode.
Yeah, I think it's...
Oh, this seems to be what's happening. So there I am in presentation mode, flipping, and apparently it doesn't... Can you see this?
I think if you just click down on the next slide, we'll be able to see it.
Okay. Oh, wow. I was
Warren, I found if you stay out of presentation mode and just move the screen down.
Just
I had the same problem, exactly.
All right. So here's my years with the wind. Here's my 30 days of wind. Can you guys see this?
We're still seeing your first slide. So if you try to exit presentation mode.
I'm out of presentation mode. Now I'm just in.
Then just use your mouse and pick the slide down below. Yeah, there you go.
But that's what I'm doing.
Oh, click it though.
Yeah, I'm not sure what I'm doing wrong.
Okay. Well, we're still seeing your first slide. So
I'm in slide sorter mode with the main slide. I'm now in the same mode that the rest of you guys were in.
Mm-hmm. We've got a suggestion.
I can see your sidebar. I can see it too.
If you could try unsharing your screen and then resharing again, maybe maybe that will fix the problem.
Okay, so I unshared, reshared. Okay,
Sounds like you've got some great images for us. We'd love to see them. Yep. Okay, so now we're on your fourth slide. Yep.
Fourth slide?
Yeah, it says PSE&G solar farms.
All right, well that's weird because now I'm moving the ramp. Am I still on the?
Yep.
Okay, am I on the 6th slide?
No, it's still on the 4th one. So I think there's something going on with the advancing. Yeah. So why don't you just continue and we can come back to maybe some of the individual slides later if you need them for a specific point.
But I can't. Oh, that's really a shame because now, in other words, it's only picking up whatever slide I'm on at the time. Do you see the 99.9% renewables?
Yes, that's the one we're on now.
Okay, but now I'm on the next one, and you're saying that's not moving?
No.
Okay, I'll just have to talk it through.
Okay,
so
thank you.
Yeah, sorry about that. I thought I was doing what everybody else was doing. So what we've been doing is modeling wind and solar at the level of the PJM interconnections farm. There's two types of variability you have to deal with: the predictable variability, like the sun setting, and the unpredictable variability, like wind doing what wind does or clouds coming over. There's studies that have been done. I think the slide in front of you is advertising 99.9% of energy from renewables. This was done by a group that I've been working with, headed by Willa Kempton. Now, this was a very simple model, and it illustrates that when you use a very simple model, it's like, oh yes, we can get 99.9% of our energy from renewables. So the problem, and even the Department of Energy has been doing, very simplistic studies where they'll say, oh, well, there's this capacity factor, which is when you take the total capacity of, say, a solar farm, divide it by what you get, and you may say get a number like 20%. Well, if you make it big enough, 20% times a big number is a lot of solar energy. But it ignores the fact that the sun sets. One of the lines I love is to ask, how many homes can 10 megawatts of solar panels power? And the answer is 0, because without the grid, you can't handle the variability. So we've been doing a number of studies of wind and solar, and I'm going to unshare my screen and then share it again, because there's one slide that I'd like you guys to see. See my value of storage?
Yes.
Okay, cool. I'm not even going to attempt to put this in animation mode. So the black line there is showing the variability of energy due to solar. Those blue things are Tesla Powerwalls. And if you invest in one Tesla Powerwall, you can see it's very heavily utilized. But with every additional Tesla Powerwall you put in, you use it less and less. And so what you get is that when you want to use batteries to handle the variability due to the natural with renewables, the problem you'll run into is the marginal cost rises dramatically as you try to get. So if you just put one Tesla Powerwall in your home, depending on your home size, it might give you about 4 to 6 hours of power when the sun is down. But if you put the second Powerwall in, you're going to get a little bit less. And each additional Powerwall gives you less, but it costs the same. So your dollars per kilowatt hour of energy rises dramatically. And the energy community that gets all enthusiastic seems to ignore this, but you talk to any company who actually has to invest in energy storage, and they'll say, well, we'll do a little bit of storage, but we can't do too much because on the margin it gets expensive. So the economics of energy, and especially renewables, is very interesting. You've got to deal with predictable variability. The unpredictable variability means you need a lot of backup power. This has generally been ignored. My models, we've gotten as high as 20 to 25% energy from renewables, and then things start to get complicated. So I love hearing the projections of getting to 50%. Germany's gotten to 35%, and they're really running into a cost curve. So be curious to hear everybody else's comments on this.
Great, thank you, Warren. So now we will get into some of the audience questions. A reminder for everyone viewing online, you can submit your questions in the form just below the video feed. So the first question we have has to do with a couple of types of battery technologies. And the question is about flow cell versus conventional technologies. This comes from Robert in California asking, for grid scale storage, flow cells are attractive since they scale arbitrarily, but conventional cells are enjoying rapid improvements driven by the electric vehicle market. So looking in the next 5 years or so, which of these technologies are likely to become more dominant? Would any of our panelists like to tackle that one? We can move on if we don't have any takers, any experts on that particular point.
I have to admit, I was hoping one of the hardware guys would pick up on this.
No, so
I defer to Ethan on that. He's more of an electrochemist than I am, but I can pass.
Yeah, so I'll step up a little bit, and I'll give a very unsatisfying answer, which is essentially that I think the jury's still out. There's definitely in the short term, if you had to make a decision for a solution today, right now, in this moment, the advantage does go to the conventional batteries. However, that's just because there's been larger infrastructure investment already established in terms of manufacturing and creating these units and systems. Case in point is, as Warren said, is the Tesla Powerwall, for example, right? That's there, you can buy it today. There is a strong argument that is being vetted and figured out with regards to these redox flow battery systems, and this is something that is currently a significant effort and driver to try to get there. And so there's a lot of great work and science to be developed, and part of it will come with a coupling between both technology and the kind of economic modeling that even Warren is kind of doing, because essentially what you need to do is get to a situation where these more newer technologies are right now for sure more expensive. And so you need something that will help balance that out, and that's going to come from kind of an economic balance and a tie towards technology.
Well, and kind of a follow-up question on that is, if we're talking about grid scale storage and the planning that utilities do, I mean, that usually happens kind of many years, if not decades out. And so how does that wrinkle play into those technology decisions that are happening as contracts are being made now for technology that is developing very rapidly?
So if I could, the issue of grid scale storage is, I love to hear about the Tesla Powerwalls. The economics of grid scale storage is always better. It's always better to put a big thing on the grid. The interest in the Tesla Powerwall is partly because people with a little bit too much money on their hand are just entertaining themselves. But there's also the artificial economics of behind the meter versus in front of the meter, because to the extent that I can save my energy bill behind the meter, here in New Jersey, I'm saving 17 cents per kilowatt hour, but in front of the meter, I'm only saving myself 2.5 cents per kilowatt hour of actual energy costs, because most of what I pay in utility is not for the actual energy, it's just to help them maintain the infrastructure.
Interesting.
So while we're on the issue of grid scale storage, we've got a question coming in from Karen in Massachusetts, who's actually asking, pivoting over to reliability, grid reliability. And so I'm interested in particular, Warren, maybe you could start us out, and then we can open it to the other panelists about how increased renewables penetration affects things like large scale reliability at the grid level.
Well, so right now, the renewables seem a lot of fun because with all the variability, it's not really a lot of variability. The grid can handle the variability at the level it is now. PJM has 5 gigawatts of wind capacity, but that's on a 100 gigawatt system. And they're not actually getting 5 gigawatts, they're getting more like 1 or 2 gigawatts most of the time, but sometimes hitting 5. That type of variability PJM can handle. The people who want to get 20 to 30% of their energy from renewables, that's a whole lot more variability. And now we do have the issue of grid stability. I think a lot of the models that are claiming that we can get, so there's a well-known professor, Mark Jacobson in Stanford, who's got a nice website at thesolutionsproject.org, who will claim that pretty much anybody could get 100% of their energy from renewables. My Brazilian colleagues will enjoy seeing that his year 2050 projection not only has Brazil getting 100% from renewables, they're getting only about, I think, 10% from hydro. So that's a bit of a head scratcher. It's going to be a problem. Germany is a great case study because they're up to around 35%, and they're having to do a lot of backpedaling. They're using a lot more coal to handle the variability. They're starting to run into a lot of problems. They're hiding the costs by putting it in through taxes. I think somewhere between 20 and 30% here in the United States, we're going to run into a lot of problems. Again, unlike countries like Brazil, that are in a completely different setting with all their hydro. I think Brazil can do a lot more with wind, and they are, because their hydro is such a great backup asset where you can handle a lot more variability. It's a lot easier with hydro. Everybody's got a different story. Like Hydro-Quebec would have a lot easier time with hydro. Of course, they've got all that. They'd have a lot easier time with wind. Of course, they've got all that hydro. I was texting Michael off to the side going, well, how much hydro does Saskatchewan have? And apparently not very much.
Yeah, that's a very good point, Warren. I mean, in Saskatchewan, we don't have that much hydro compared to a number of other provinces. So we're still, I mean, Sask Power has ambitious targets on renewables, but we're still right now baseload coal and natural gas, about 50% each on those. And so it'll be interesting to see how, whether these kind of targets are achievable. I mean, the desire is there, but there's technology issues too, right? And economics.
It's going to get hard. It's harder than people think it is. Everybody says solar's good, solar wind, but that's because we have a grid that can handle the variability. But if you start getting north of 20% penetrations, you're going to start having difficulties. It's not going to be easy. It's going to get expensive.
On that topic, we've got a question. Actually, this is coming from the the perspective of a grid participant or grid operator, the decision to go for having a natural gas peaker plant versus having battery storage or other grid scale storage, could you address that decision? And at what point will batteries be a better sort of complement to renewables than natural gas peaker plants? Or will that ever happen?
Okay, so first of all, you have to understand, I love to look at Wall Street as if you ever want to run into somebody who really knows how to deal with uncertainty, talk to Wall Street because they're good at it. If you ever want to talk to somebody who's really, really good at handling peaks, talk to the energy industry. They're masters at it. So the thing is, with their peaker plants, those peaker generators are really economically tuned to be peakers. So high fuel cost, low capital cost. Those generators are economically designed to be peakers. You don't care if they're inefficient because you're not going to use them that much. What you want is a low capital cost. So the problem with batteries is batteries are batteries. There's no such thing as a peaker battery, to the best of my knowledge. So we haven't gotten to the point with batteries where we have, to the extent that you're going to use that battery a very small percentage of time, that's still quite an expensive battery. So, I know that California's been pushing into batteries very heavily. Most of the batteries on the grid are pretty much used for one of two reasons. One is something called frequency regulation, which has nothing to do with renewables. That just has to do with power stability. And the other is very special load pockets. Like a great example is Eastern Long Island that has a few dozen hours, maybe 20 or 30 hours a year where they just can't meet that summer peak. And either they build hundreds and hundreds of millions of dollars excess transmission, or they put in a big battery, or they actually are starting to invest in wind farms off the end of Long Island. So I think using batteries instead of peakers, obviously if they come down enough in cost, but they're not known for being cheap.
Yeah, everything always comes back to cost, it seems. We've got a couple of questions on some of the less well-known storage solutions that are out there. So Steve in New York asked about compressed air in underground caverns. And then we also had a question from, I believe, Tom in Massachusetts about underground water flow in mines, and then also kind of trains, pulling those up on hills and using that as storage. So just thoughts from the panel on some of these non-battery types of storage, and are any of those ever going to become feasible, economically feasible?
Okay, I've heard about some of those technologies. I've got a colleague.
We'll get back to batteries in a second here, while we've got our battery chemist expert.
I was interacting with a colleague of mine, Rob Stocklow, who's famous for the wedges co-author on the wedges article that's pretty well known of how to close the gap with CO2. The sense is that all these technologies are great. It's mainly mechanical engineers going, this is really cool. And they're initially just focused on does the technology work? And it's sort of a couple steps down the road before they say, well, how much does that actually cost? And so, like here in PGM, they do have a pumped hydro facility. They pump uphill at night and pump downhill during the day. It's of no value at all for handling the variability of wind and solar. But those are facility is very, very specialized. It's not very easy to build those. Compressed air is going to be something similar. You're going to need a big underground, an old coal mine or something like that. So you need very unique settings to come up with that. Let me see. You were also the one about putting a rail cars up.
Train on a track. Yep.
I saw that. I cracked up. I'm like, again, this is a really creative mechanical engineer coming up with these ideas. I'm just really worried about scale. I haven't seen any numbers on that.
Yeah, so maybe it would work in very specific areas, very specific geographies, but we're not going to see those all over the place.
The thing about energy is incredibly local. Everybody's got their own story, and it's like the New England, the United States, very different than Mid-Atlantic, very different than the Southeast. Go to Brazil, completely different, and even within Brazil, you've got the different areas of Brazil. I mean, everybody's got their own story.
Great, so let's get back to, we've got a bunch of actual kind of battery chemistry and material science questions that I want to make sure Ethan gets a chance to address here. So I think this is just a kind of a good general question for getting us, for those of us that don't know very much about battery chemistry. So Hani from Washington is curious about what makes batteries explode and what have we learned from the Samsung Note 7. So from a consumer perspective, are batteries safe, and how are things going there on that front?
That's a very topical question. So batteries are relatively very high. You know, as we know, they're running our portable electronics, our devices. There's a lot of energy within these battery technologies, and so it's, you know, the initial ones that are being used and really most successful, they are really safe when you stay within certain operating conditions. And essentially, what was discovered with regards to the Samsung is they were definitely pushing the boundaries, and there was a coupling between, I would say, chemistry and product design in terms of, you know, people don't realize, but your batteries actually swell. They change in size a little bit as they are operating. They heat up, they cool down. So there's a lot of different physics that are taking place when a battery is operating. And if you put a battery in a sealed case and it's completely no room to expand, it's going to compress the battery. And that's where essentially what was one of the findings in the Samsung case. And so in general, as long as people are not pushing the boundaries too much, mechanically, materials, also potential, the amount of the voltage they apply to a battery will be in a safe realm.
Great. We had another, so Ethan, while we're on you for a second, so we had a question from Stuart in Massachusetts asking if you're hopeful about new research on hydrogen metal with no electrical resistance. So I'm gonna toss that one over to you because I'm actually not familiar with what this question is about.
So this is one of the newer ones, which I was just reading a little bit about in terms of, I heard about this. I didn't read the article explicitly. So the thing I don't know is what they were planning to use this for in terms of this phase. And, you know, of course, the conditions that were used to create this, I think, were rather extreme. So it's much more on the very early stage of science. And my understanding was essentially a very interesting discovery of a property phase of hydrogen that was previously not determined. And so that's the kind of the beauty of basic energy science and basic science in general, is that you can make these new discoveries, and it might not be clear what its application will be right now, but once we start to prove that these materials or phases can exist, then we can potentially discover their utility and function in the future. And so I think any new discovery that has not been found before is always interesting, and we'll have to see how it plays out.
Great. So we are having so many questions come in, which is really exciting. So try to get to as many as we can. We only have a few more minutes. So we did have a question about innovations happening right now in UHVDC, which is ultra high voltage direct current transmission lines, and how any innovations happening in that realm may actually help with that variability problem. So this is looking at long distance transmission and whether that can actually help even out some of those, some of those blips that we see in the grid at the local level.
Warren can probably comment on the economics better than I, but I do know that that's something being pursued for sure by Hydro-Quebec, and actually was done in the former Soviet Union a long time ago in Siberia, places like that. And then, you know, for a long time, I mean, we teach in basic physics that AC is great, and this is what led to Westinghouse's AC system being preferred to Edison's DC system, because you could change the voltage level easily with a transformer and relatively efficiently. But now, with modern power electronics techniques, that advantage is not necessarily so big anymore, and it turns out you can get very high efficiency with very, very high direct current, high voltage lines. So it's an interesting area for sure from the technological point of view. I don't know about the economics, but the potential for higher efficiency is there, I believe.
And are there any projects where there, some direct current transmission lines have actually been installed in Canada?
Actually, let me see. I have a little. Let me try to find a graphic here that I had.
I think there was one on Long Island, maybe that I'm familiar with.
There may well be. I'm just looking here. Okay, I'm going to try a screen share.
Our favorite piece of Google Hangout technology.
It's a PDF, so maybe it's better. I don't know, but this is a report from the Canadian Electricity Association, based on, I think, numbers from the National Energy Board in Canada. This shows some of the transmission lines currently. So you can see most of them are low voltage. I mean, we have a piddly little one to North Dakota, I guess, with 230 kilovolt, which is not much. But in Quebec, you've got 765 kV. And now I think they're pushing, I think 900 kV or maybe exceeding a megavolt, I'm not sure. So, but whether those are, those might be research projects still at this point. But probably that's something Warren is much more knowledgeable about.
But it is the case that these HVDC lines, I'm not familiar with the ultra high voltage, but there's places where it mainly with wind, also with hydro. New England loves to purchase Canadians hydro. They've got more than they need. We love it. We've got those areas in the middle of the United States that are very, very windy. Right now there's lines under construction to bring some of that east. So there are opportunities. I don't think this is going to be a big solution, but there are pocket opportunities that people are exploiting to, say, get wind from the Midwest or hydro from Canada. And so I think what we're going to see is, at the end of the day, that the HVDC lines are going to be, they're going to be in the solution. They're going to be used. I don't think they're going to be the great solver. I think we here in the mid-Atlantic states, where we have all these people and not much wind and some sun.
Actually, I just found this little graphic here, same report. And I misspoke a bit because the lines I showed are not DC, of course. They're AC and reaching the upper limit of AC. But there's a Lake Erie connector in Pennsylvania. There is a Vermont to Quebec line that's a megawatt. A high voltage DC. And then there's also this Northern Pass. So there's some. These are delivering renewable energies from Quebec to Vermont and also into New Hampshire, New England. So. And they're under construction. They're going to be completed in 2019, apparently. So for what it's worth, there's something from a recent report that talks to that.
Great, thank you. So
you can see it. I don't know if you can see that.
Oh.
But.
Yeah, we can read that well. Thank you. So we are unfortunately coming up against the end of our time, and this makes me sad because we are getting so many amazing questions that we are not going to have time to. So for those of you watching online, we will pass all of the questions with your emails on to the panelists, who will have a chance to respond to those offline. We've got some great questions about very specific battery technologies, about the ability of grid storage to help in case of an attack or something that might threaten the grid, questions about climate change, and all kinds of other great topics that we did not get a chance to cover. So knowing that your questions will be seen by the panelists, I'm going to give each person an opportunity to end by we've talked about so many different innovations, so many changes that are happening in the power sector right now. So I'd like each of you to pick kind of the one thing that you're seeing, either within your field or in a related field, that could be the most paradigm shifting in the next 10 years. So what are you most excited about? What are we looking forward to in terms of changes in the power sector? So why don't we start off with Michael, your final sort of innovation that you're going to be focusing on in the next few years.
Oh yeah, that's an easy one. And I'm not really a grid guy. So the thing that's most interesting to me is really on the generation side, and the prospect, not guaranteed of course, but the prospect of controlled nuclear fusion. And I will just say that, and it's probably longer than a 10-year time scale, but we're in an interesting era right now because people probably know about the ITER fusion reactor under construction in southern France. It's an international project. But at the same time, we have many companies, private venture-funded companies, in the US, in the UK and Europe, and also even in Canada, working on different approaches to controlled fusion. So there's Tri-Alpha Energy in the States, there's Helion Energy is another one, Lawrenceville Plasma Physics, there's a company called Tokamak Energy in the UK, and then we have something called General Fusion in British Columbia. So I'm not, of course, I mean, one can't bet on fusion 100%, but it's an interesting time in the field because it's not just putting all the money into this one reactor. There are these other things going on, and there are different kinds of nuclear fusion energy, not just the ordinary one that produces lots of neutrons. There is aneutronic fusion, which is can be harnessed to actually give direct energy production, electricity production with no neutron flux. So there's a lot of interesting things happening in the field. And if you're somebody that looked at fusion, I'd say 20 years ago and maybe said, okay, it's not going to happen, it's kind of interesting to look at it now because there's a lot of interesting things happening. And that's
great.
That's my plug. So
yeah, sounds like we could have an entire follow-up panel just on fusion.
You probably could. Yes,
we will put in that request. All right, Warren, let's go to you for your kind of innovation that you'll be watching and what will be the most paradigm shifting in the next few years.
Okay, so my pet topic is driverless fleets of electric vehicles. The economics of this is compelling. Electric vehicles are just cheaper to operate. The lower cost, the driverless fleets have this tremendous potential for lowering accident costs and insurance, and there's this mega thing of the parking problem that goes away. If you have a driverless fleet, you don't need a 300-mile battery. So suddenly the whole issue of hauling around really big batteries goes away. I think this is going to be the biggest shift, and if you look around, you realize I'm not exactly the only person who thought of this. And I think that the implications of this are so wide-ranging that at one point here at Princeton, I said, I'm not really sure if I can think of a department. I said, well, maybe the English department. And there was a professor from the English department there that says, oh, no, that's very important for us too. It touches every aspect of life. Now, none of this has to do with, green and global warming. That's a byproduct that we get that benefit from. It's going to have implications for the grid. Suddenly, we're going to have many millions of batteries running around just because it's a better way to go. And oh, by the way, they're batteries. And suddenly, this whole issue of the cost of storage might vanish under the economics that this whole vision is so compelling. So that opens up a tremendous opportunity to, suddenly have, free battery storage. I don't know. I think that's a fun one to think through.
Great. And finally, Ethan, you get the last word here. What innovation are you really focused on? What are you excited to see in the next few years?
So myself personally, I'm very focused on interfaces and the interfaces between mediums. I think we're going to find new science, new physics, new understanding that hasn't really been unearthed yet. And so that's really what we're trying to tackle and drive for. But I think when you tip this in the broader perspective about energy and grid storage and everything, we've heard a lot from the panelists today, and I think the beauty of where we are with regards to energy technology and going forward is there's a lot of options that are being explored right now, a lot of different avenues, and there is no single shot that's going to do it. And so we're seeing a distributed effort and approach to trying to do this. It's going to be local solutions, global solutions, a lot of different topics and directions. And I think it's great that we continue to support and champion a lot of these, not just pick one winner, but we really try to do a lot of distributed ideas because it's going to take a lot of them and different ones to kind of move forward in the future.
Great, thank you. So that is all the time that we have today. So thank you, panelists, for an amazing discussion. And on behalf of the Alumni Association, thank you everyone who tuned in to our Faculty Forum Online Alumni Edition. Again, our panelists were from the University of Saskatchewan, Lawrence-Berkeley National Lab, and Princeton. We did not get to all of the great questions that you submitted, but we will pass those on to the panelists who can see them and get a chance to respond to them. You can also tweet about today's panel using the hashtag MIT Better World. Send more follow-ups or any feedback you have about this session or any of the online panels that we do. You can send those to alumnilearn@mit.edu. All right, thanks again, everyone, and goodbye.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.